Hello, this is Mr. P, and today we're going to learn about solving trigonometric equations. The first step for these solutions is you want to manipulate the equations so that you get a function of an argument equals a value. For example, you want something along the lines of the sine of theta equals 1/2. To get there, you want to use your algebra to isolate the trig functions. You may need to use identities to combine or switch out one function for another. The Pythagorean identities are very helpful in this regard. Or you might have something that's not a linear equation, so you might need to set it equal to 0, factor, and then set each factor equal to 0. But the goal of this is, of course, to get the function of an argument equals a value. Once you have that, then you can use your ideas of inverse trigonometric functions to find the value of theta that's going to satisfy the equation. Now for general solutions, because some of these equations have an infinite number of solutions, so for the general solution, we're going to find the values within the period of the function, and then we add the periodicity. So for the periods of the functions, we need to know that the period of sine is 2 pi, the period of cosine is 2 pi, and the period of tangent is pi. It's important to know those. We'll be using those a lot. Sometimes you're going to have an argument that is not just theta. It might be the sine of some expression. In those cases, you may need to do a little extra work. You may need to find the general solution first and then find some specific values by plugging in integral values for your k or your n, and then you're going to list the ones in the solution set that are in the interval you're looking for. Also, very importantly, you want to check for extraneous solutions, especially when squaring both sides. But a good rule of thumb with any algebraic equation is that if it's not a linear equation, then you treat all solutions as potential solutions until you check them in the original equation. Those are just good words to live by mathematically. Now, also when you're using a calculator, there's a little limitation to some of the calculators. It will only give you one of the values within the period when you're using the inverse cosine, inverse sine, or inverse tangent buttons. So we have to make an adjustment for this. If we find the first, like let's take sine for example, if we find our first answer, then the second answer is going to be pi minus that first answer. The reason we can see visually in our circles here, both of these triangles have the same value of sine. If this was a unit circle, then sine would be the length of this segment, and we can see both these triangles have a positive sine, and they both have the same magnitude. So for cosine, these two triangles would have the same cosine, so the adjustment here would be 2 pi minus our first answer gives us our second answer. And for tangent, these two triangles have the same tangent, so it would be pi plus our first answer would give us our second answer when doing the arctangent. So we'll see these in the examples, of course. So speaking of, let's start out with our first example. This is our most basic trig equation. It's already in the form we want, which is a trig function of an argument equals a value. So what we want to do here is we want to think to ourselves, what would be the angle whose cosine is 1/2? And you can do this visually by drawing the triangles, but you see that cosine is positive, so within the period of cosine, which is 2 pi, we're going to have two places where the cosine is positive. That would be in either quadrant 1 or quadrant 4. So the triangles would look like this. If you think of cosine, you can assign the values using your SOHCAHTOA. So cosine is adjacent over hypotenuse. So adjacent would be 1, hypotenuse would be 2. And then hopefully you should recognize the special right triangles as a 30, 60, 90. So you know the other side is root 3. Or you might just do the Pythagorean theorem to find the square root of 3 and then recognize it's a 30, 60, 90. Now our reference angle, since the 30, 60, 90, our reference angle is opposite the square root of 3, that makes our reference angle the 60-degree angle, or in radians that would be pi over 3. Same reference angle for the red triangle would be pi over 3. However, we're not looking for the reference angles, we're looking for the actual angles here. So we want to look at our angles from 0 to 2 pi as positive angles going from the initial side to the terminal side. So for the blue triangle, that would actually be the same as the reference angle in the blue triangle. That would be pi over 3. And then for the other one, we want to look at the angle from, again, initial side to terminal side. And we can see that within the period of 2 pi, the argument is going to be either pi over 3 or 5 pi over 3. So therefore, once we know those two values, we set up our general solution by saying that the general solution is going to be the argument is equal to the angle plus that periodicity. Or in other words, the argument, which is theta, is equal to the angle plus 2k pi. Or the argument is equal to the other angle plus 2k pi. We have two possibilities here. And if you think about this visually, it's this periodicity gives you another revolution around the circle. So 2 pi is the period. So k times 2 pi, k represents any integer, positive, negative, or 0. So it would just be any, if you add or subtract 2 pi to the terminal side, you're going to get a coterminal angle, which will have the same value of cosine. So we write it as plus 2k pi, and k can take on any integer value. Now this is our general solution. It shows a way to describe the infinite number of solutions. It shows the pattern. But if we had some sort of restriction, like let's say we wanted the solutions just from 0 to 2 pi or some other interval, then we can take the general solution and we can substitute in integral values of k to get some particular solutions. And we'll see that a little later as well. But our general solution we would write with the plus 2k pi. Some textbooks use 2n pi. It would be the same thing. K or n just takes on an integer value. All right, let's look at our second example. Now we get to do a little bit of algebra here. We don't have the trig function isolated, so we need to first move the square root over to the other side, and then we're going to divide both sides by 2, and now we have sine theta equals negative root 3 over 2. So a function of an argument equals a value. So now we're thinking to ourselves, what is the angle whose sine is negative root 3 over 2? Well, let's look at it visually. Sine would be negative in quadrants 3 and quadrant 4. Because sines are y values, so if y is negative, we're going down, and that would leave quadrant 3 and quadrant 4. So if we label our triangles, then we can recognize them as 30, 60, 90 triangles. The reference angle would be 60 degrees because it's opposite the root 3, so that is pi over 3. But again, we're not looking for the reference angle, so we're looking for the actual angles. For the red terminal side, it would be pi plus another pi over 3 would be 4 pi over 3. And for the blue one, it would be almost 2 pi. It would be pi over 3 less than 2 pi. So 6 pi over 3 minus 1 pi over 3 would be 5 pi over 3. So our two angles would be 4 pi over 3 would be the red one, and 5 pi over 3 would be the blue one. Notice how here we don't have any periodicity because we don't need it. They just wanted solutions from 0 to 2 pi. And looking in the entire circle, those were the only two solutions. So we don't need to add plus 2k pi to this. Okay, for our third example, now we have an argument that is not just theta. So we're going to see that extra little bit of work we're going to need to do. First of all, it is already in the form that we want. It's the function of an argument equals a value. So visually, we want sign to be positive. We know that that's going to happen in quadrants 1 and 2. So this is what the triangles would look like. And we should recognize by now that this is a 30, 60, 90 triangle. However, this time our reference angle is the 30-degree angle because it's opposite the 1. And therefore, within the period of sine, which is 2 pi, the arguments need to be pi over 6 or 5 pi over 6. However, those are not our answers. Even though we're just looking from 0 to 2 pi, those are not our answers yet because our argument is not just theta. Notice how our argument is being multiplied by something. So in effect, we're multiplying inside the function, which means it's going to affect our function horizontally, which will change the period. So we can't just take these two. We want to look at the general solution and then find out which values of k will give us values within this interval. We have to do this because if we change our period, we can't just automatically assume these are the only ones within 0 to 2 pi. So looking at the general solution, we're going to say that the argument is going to be is equal to the angle plus the periodicity. So here our argument, which is 2 theta, is equal to the angle plus the periodicity. Since we're dealing with sine, it's 2k pi. Or the argument is equal to the other angle plus the periodicity. And of course, to solve this for theta, we just divide through by 2, and you get theta equals pi over 12 plus k pi. Notice how the periodicity has changed, which should make sense because our period changed. Also, we notice that it is counterintuitive, like we've seen before. If we're multiplying, you'd think it would make it bigger, but it turns out we're making it smaller. So once we have our general solution, now we want to plug in values of k so that we can find values that will fit within 0 to 2 pi. A little bit of logic will show you that pi over 12 and 5 pi over 12, if you look at the fractional parts, 1/12 and 5/12 are less than 1. So if k is any negative number, then it would in effect be subtracting at least 1, which would make both of these negative, and that would be outside the range. So we don't have to worry about any negative numbers. We can start at 0, and plugging in 0, we would get pi over 12 and 5 pi over 12. Then if we plugged in 1, we would get 1 plus 1/12 would be 13/12, so 13 pi over 12. And 1 plus 5/12 would be 17/12, so it would be 17 pi over 12. Would be 2 more solutions. But then if we plugged in 2, notice how this would be 2 pi plus anything positive would put it outside of this range. It would be too large. So -1 was too small, 2 was too large, but 0 and 1 are just right. So therefore our solution set were the 4 values that we got by plugging 0 and 1 into the general solution. If we try to plug in anything higher than 1, it would go outside the range to the right, and anything negative would be below the range. So this is our solution set, and when we write the solution set, we want to generally write them in order. That's the normal convention. All right, if we look at example 4, now we can deal with some tangent. We've been doing sine and cosine. Tangent can often be easier as long as you treat the period correctly. First of all, this is already in the form we want. It's the function of an argument equals a value. So to look at this visually, I should recognize that my period for tangent is pi. So I'm looking from 0 to pi. I only care about quadrants 1 and 2. And since tangent is positive, that's going to occur in quadrant 1, so there's only one triangle to worry about. If the tangent is 1, that's the same as 1 over 1. So tangent is opposite over adjacent. So we can write opposite and adjacent would each be 1. And then you should recognize the triangle as a 45, 45, 90. So therefore our angle would be pi over 4. Within the period of pi, with period of tangent, which is pi, the argument is pi over 4. So in general, we want to have the fact that the argument is equal to the angle plus the periodicity, and this is where the common mistake is made. Notice how the periodicity is k pi for tangent, not 2k pi. 2k pi you use for sine and cosine, but k pi is what you use for tangent. Then to solve for theta, just add pi over 2 to both sides, and we get theta equals 3 pi over 4 plus k pi. All right, number 5. Let's look at what happens with a calculator. For this one, we have sine of theta equals 0.3. That's not one of our special values on a special right triangle, and it's not one of our quadrantal values. So we are going to need a calculator here. They want you to express it in radians, rounded to 2 decimal places, so make sure your calculator mode is in radians. If you're in degree, you will get the wrong answer. Now we need something to plug into the calculator. So if we take our original equation, and we take the arc sine of both sides, then the arc sine of the sine just gives us our theta, and we have an expression now that we can plug in. That'll go into our calculator. But don't forget the adjustment we need to make that we talked about earlier for sine. Once we find one of the values, then we can find the second one by doing pi minus our first answer. And the visual here shows why. Now, if we go to the calculator, we're going to put in the arc sine of 0.3. That'll give us that decimal. And then we're going to take that answer and we do pi minus that answer will give us our second answer. And the answer, recalling the previous answer on the graphing calculator, is the second function of the negative sign. So the keystrokes will be pi minus second negative enter, and that'll give you the second value. But of course we're not done yet. We have to answer the question being asked, which means we need to round this to do 2 decimal places. So therefore, theta is going to be equal to 0.30 or 2.84 radians. Make sure you round it properly. All right, example number 6. We're going to look at something that is not a linear equation. We need to do a little more manipulation here. You should recognize this as a quadratic. And as a quadratic, our first line of defense is we want to, of course, set it equal to 0 and then factor it. Now it's already set equal to 0 for us. And when we factor it, we should factor it as 2 sine theta minus 1 times sine theta minus 1. And the idea we're going to use here is the zero product property. If you have two things that are multiplied together and the result is 0, that means that one of those two things must be 0. So either the first factor is 0 or the second factor is 0. So now we have 2 trig equations, which doubles our fun. That's a good thing. But these are very easy ones to solve. On the first one, we're going to isolate the trig function. We just add 1 to both sides, divide by 2. On the second one, the algebra is even easier. We're simply going to add 1 to both sides. That gives us sine of theta equals 1/2 and sine of theta equals 1. For the first one, we can look at that visually by recognizing that these are values in the special right triangles. So I'm going to use the triangles for this one. Sine is positive in quadrants 1 and 2. So these are my triangles. I should recognize the 30, 60, 90. My reference angle here is the 30-degree angle, or pi over 6. So I should recognize that the angles for the terminal sides are going to be pi over 6 and 5 pi over 6, respectively, for the blue and the red triangles. For the other equation, this is a quadrantal value. So I think it's easier to visualize those using the graph rather than the triangles. So if we think about the graph of sine, the first cycle of the graph of sine, the question is where is sine equal to 1? Well, that equals 1 at the top here, and that's at pi over 2. So pi over 2 would be the value for this equation. Now, these three answers, and remember, we're looking at 0 to 2 pi, so we don't need to add any periodicity here. But these three answers are only potential answers until we verify them in the original equation. But when you do verify them in the original equation, all three of them do check out. So therefore, our solution set is pi over 6, pi over 2, and 5 pi over 6. Make sure you write them in order. Okay, example number 7 is another fun equation. We have 3 cosine theta plus 3 equals 2 sine squared theta. Immediately what comes to mind when I see this equation is that we have a cosine and we have a sine. We have two different functions. That's not what we want. We want function of an argument equals a value. So we have to find a way to switch out one for the other. And the fact that sine is squared means we can easily do that using the Pythagorean identities. Therefore, instead of sine squared, I'm going to replace that with 1 minus cosine squared, of theta, that is. And that way we have everything in terms of cosine. So a little bit of algebra now. This is a quadratic equation, second degree equation. So I'm going to distribute and then set it equal to 0 by moving everything to the left side. That gives me this trinomial, which we can now factor. And once we factor, we're going to set each factor equal to 0. So on the first one, we're going to set the factor equal to 0, and then we are going to isolate the trig function by subtracting 1 from both sides and dividing by 2. For the second one, the algebra is even easier. We're just going to subtract 1 from both sides. So again, these you should recognize as special right triangle values. So the visualization for the first one is going to be the triangle. Cosine is negative in quadrants 2 and 3. And my values of the angles, if you recognize the 30, 60, 90 triangle, my angles are going to be, for the blue one, will be 2 pi over 3, and for the red will be 4 pi over 3. The negative one you should recognize as a quadrantal angle. So if we look at the graph, you're going to have cosine is negative 1 right in the middle, which is at pi. So that will be the value for that one. Again, these are just potential answers until we check them in the original equation, but when we do plug them in, you'll find that they all do check out, so therefore our solution set is 2 pi over 3, pi, and 4 pi over 3. All right, for number 8, we have another equation with pretty much the same thing here. We have cosine and sine. I don't want two different functions, so we need to try to find a substitution. Again, cosine is the one that is squared, so that makes an easy substitution. With cosine squared of theta is 1 minus sine squared of theta. These Pythagorean identities do come in handy. And now everything is in terms of sine. So we're going to set this equal to 0 and then factor. Now, algebraically, I personally don't like negative leading coefficients, so I'm actually moving everything to the right, and then I just flip the sides. So I get sine squared theta minus sine theta plus 1 equals 0. And then, to me, that would be easier to factor. So for factoring, we want factors of positive 1 that add up to negative 1, but there are none. Now that doesn't mean we're done with the problem. There's a misconception going around that if you can't find the factors, then there's no solution. That just means we can't factor this using integers. So we still look at the quadratic formula because there might be radical solutions to the equation. So the quadratic formula, if you recall, is that. And if we look at the expression underneath the radical, that's called the discriminant. The discriminant will tell you what types of solutions you have. If you have a discriminant that's positive, you'll have two real solutions. If your discriminant is 0, then you'll have one solution. It'll be a double root. And if you have a discriminant that is negative, you're going to have two complex solutions. So when we use our values from this equation, we'll see that A is 1, B is negative 1, and C is 1. So we'll notice that the discriminant is negative because if we plug those in and evaluate, we get negative 3 for the discriminant. Therefore, there are no real solutions. There are only complex solutions. And right now, we're only dealing with the real solutions. So therefore, this problem has no solution. But it's important to note, it has no solution not because we couldn't factor it. There might have still been radical solutions. It has no solution because our discriminant was negative. Okay, number 9, something else that can come up. Let's say we have sine plus cosine equals 1. And same situation here, I have two different functions. But here, neither of them is squared. So I can't use a Pythagorean identity to switch them out. So if neither of them is squared, then one thing we can do is square them. So I'm going to square both sides of the equation, then I'll have some things that are squared. Now don't fall into the common algebra trap here. A plus B quantity squared does not equal A squared plus B squared. A plus B quantity squared is A squared plus 2AB plus B squared. So if we expand the binomial, we should get sine squared theta plus 2 sine theta cosine theta plus cosine squared theta equals 1. And then I've underlined the sine and the cosine. You should recognize that sine squared plus cosine squared is 1. So those two combine to be just 1, and we bring down that term. Now, of course, we're going to subtract 1 from both sides. And we can even clean it up further by dividing both sides by 2. And what we have here is we have two things being multiplied where the result is 0. Now, we weren't trying to factor it, but this worked out well for us. We can use the same idea as the zero product property because we have two things multiplied together equaling 0. So either the first factor would be 0 or the second factor would be 0. So this is how we write that. Either sine of theta is 0 or cosine of theta would be 0 to give us this equation. All right, now for sine of theta, that is a quadrantal angle. So visually, I would think of the graph of sine. That would be 0 here and here. So that's at 0 and pi. So my two solutions for this equation would be 0 and pi. For cosine, I would think of the graph of cosine. And in the graph of cosine, it touches the x-axis at pi over 2 and 3 pi over 2. That's where the zeros are. So those would be my two answers for the second one, pi over 2 and 3 pi over 2. Now here's the important part. Remember that these are just potential solutions until we actually plug them into the original equation and verify them. But when we do that, you'll find that of the potential solutions, pi and 3 pi over 2 are extraneous. They don't work in the original equation. For example, if we look at pi, the sine of pi is 0, and the cosine of pi would be negative 1. So therefore, 0 plus negative 1 is not equal to 1. So that solution does not work. It's extraneous, and so we ignore it. Therefore, our solution set is simply going to be 0 and pi over 2. Okay, a final thing I want to go over, and this is a little more advanced, is we want to be careful of what we're doing algebraically, that we're not dropping solutions. Let's take a problem like this. Sine theta equals cosine theta. There are multiple ways to solve this problem, and I'm going to show you 3 different ways. But I want you to be aware of the subtleties that each way entails. So the most common way you see this problem solved is to divide both sides by cosine. That gives you sine theta over cosine theta equals 1, which we can use in identity to make that tangent of theta equals 1. So that would give us the solution that theta would be pi over 4 plus k pi. This is actually one that we've seen earlier. We don't need to draw that. And that would be our solution. And that is correct, but you do have to be careful. When we divided both sides by cosine, there's a possibility that cosine is 0. So you have the possibility of division by 0. You want to be careful anytime you're dividing by something that could possibly take on the value of 0. For example, let me show you what can go wrong in an algebra problem here. Let's say we had this equation, x squared minus 2x equals 0. Well, if we were to divide through by x, then it would reduce to x minus 2 equals 0, and therefore x equals 2. Well, that's one of the solutions, but in doing that, we dropped the other solution, which was 0. The original equation has 2 solutions, 0 and 2. The proper way to work this would be to factor out the common x, and it would be x times x minus 2 equals 0, and your two solutions would be 0 and 2. So by dividing by x, we dropped one of our correct solutions, so we would have an incorrect solution set at the end. This is something you definitely want to be careful of. It didn't affect us on this problem because the value of cosine that would cause it to be, value of theta that would cause cosine to be 0 was not one of the solutions. So when we divided by cosine, we did not divide by one of the solutions, therefore we didn't end up dropping the solution. But be aware that that can happen, so you have to pay attention to that. That's why let's look at other ways to solve that where we're not taking this chance. And the first way another way to look at it is, let's say instead of dividing, let's say I want to use the Pythagorean identities to switch one out for another. So in that case, we would square both sides. So I have sine squared equals cosine squared, and therefore I can make a substitution. Instead of cosine squared theta, I change that to 1 minus sine squared theta. I'm going to collect my signs on the left, divide by 2 to isolate my trig function, and then I have sine squared equals 1/2. So I'm going to take the square root of both sides and get that sine of theta equals plus or minus the square root of 2 over 2. And from these equations, I can get 4 answers, but when I check the answers, this is all within the first period. I can get four angles within the first period, but 2 of them are extraneous. So therefore, it's only pi over 4 and 5 pi over 4. So our general solution is going to be theta is pi over 4 plus 2k pi, or theta is 5 pi over 4 plus 2k pi. Now, because of the symmetry, pi over 4 and 5 pi over 4 differ by a value of pi. So if you were to actually combine both of these both can be combined as simply theta is pi over 4 plus k pi. These two are equivalent. So By doing it a little bit longer way, we had no chance of dropping a solution. Matter of fact, we picked up two extraneous solutions. So sometimes if you're lowering the degree of the equation, so to speak, there's a possibility of dropping a solution. And if you're increasing the degree of the equation, there's a chance you're picking up extraneous solutions. So what about a way to solve the problem without changing the degree of the equation? Well, we could use our cofunction identities for that. But then this would be a little bit of a different idea to solve because it will not be in the form of the function of an argument equals a value. So if we look at that, instead of cosine, I'm going to use the cofunction identity and rewrite that as sine of pi over 2 minus theta. So now we have sine of this argument equals a sine of this argument. So we're going to set the two arguments equal to each other, or in other words, take the arc sine of both sides. But here's where you have to be careful. As we saw earlier with the calculator example, if we take the arc sine of both sides, we're only going to get one of our solutions, so we have to adjust for the other solution. So therefore, there are going to be two different solutions. Our first solution is simply going to be that theta is equal to pi over 2 minus theta. So theta equals pi over 2 minus theta plus the periodicity. Or, if this is our first answer, then pi minus this would be our second answer. So we also have theta equals pi minus that argument plus, again, the periodicity. All right, a little bit of algebra to clean it up. On the left side, we're going to bring this theta over this side. So you have 2 theta equals pi over 2 plus 2k pi. We divide through by 2, and we get, once again, theta equals pi over 4 plus k pi. Or if we look at the other side, we're going to distribute here, combine like terms. So we have theta is pi over 2 plus theta plus 2k pi. Notice how a negative of a negative is positive. And now if we subtract theta from both sides, we have 0 equals pi over 2 plus 2k pi. Well, no matter what value of k you have, this is not going to come out to 0. So there's no solution for this equation, and this would be the solution for this equation. So handled properly, you're going to get the same solution no matter which approach you use. So in general, you always want to be cautious when you're changing the degree of an equation. You might be picking up an extraneous solution, or even worse, you might be dropping a solution that you're unaware of. So definitely choose wisely when you deciding how to do the algebra. And this is the last example, so we're done.